So what if I told you that the secret to understanding the boom and bust cycles of our entire economy was hidden inside the formula for an electrical circuit? It sounds crazy, right? But today we're going to uncover a secret connection, a formula that's been hiding in plain sight. And trust me, it might just change how you see, well, everything.
Okay, let's start with a question, a big one. Imagine you could get every single paycheck you're ever going to earn for the rest of your life paid out to you in one giant lump sum, right now. What's that number? It's a wild thought, but it's not infinite, right? Because we all know intuitively that $1 today is worth way more than $1 10 years from now.
Well, in the world of finance, this whole idea has a name. It's called present value. It's a fundamental concept that lets you take a stream of money coming in the future, apply something called a discount rate, to account for inflation and risk, and figure out what it's all worth in today's dollars.
And this is the formula they use to do it. Now I know what you're thinking, calculus, but don't worry, let's just look at what it's doing. All this thing does is add up your future cash flow over time. And that little e to the minus st, that's just the fancy math way of shrinking the value of money the further out it is in the future. S here is your discount rate. It's a super powerful tool. Now burn this formula into your brain for a second.
Okay, now I need you to do a complete 180 with me. Forget finance. We're jumping into a totally different universe, the world of a control systems engineer. They're not dealing with money. They're dealing with signals, things like radio waves, mechanical vibrations, or the electrical currents zipping around inside a computer chip.
So to understand and control these really complex signals, engineers have this kind of secret weapon. For most engineering students, it's just this abstract mathematical thing from a textbook that helps you solve impossible equations. It's called the Laplace transform.
And would you look at that? That's the formula. What does it do? Well, it takes a signal over time, f of t, multiplies it by that exact same e to the minus st factor, and adds it all up. Is a light bulb going off yet?
Let's put them side by side. It's not similar. It's not kinda like it. The formula for present value, the absolute bedrock of modern finance, and the Laplace transform, a core tool for engineering, are one and the same. They are identical. The way a banker values a company is the exact same way an engineer analyzes a signal. This has been right under our noses the whole time.
I mean, how wild is that? You have these two completely separate fields, economics and engineering, and they both independently came up with the exact same mathematical framework to describe their worlds. One for the flow of money, the other for the flow of energy.
But here's where it gets really, really interesting. There is one tiny but absolutely profound difference. For the finance folks, that S variable, the discount rate, is just a simple number, like 5%. But for an engineer, S is what's called a complex number. It has a real part and an imaginary part. It's not just a point on a line, it's a point on a map. And that leads to this completely mind-bending question. Okay, we get what a real interest rate is. It discounts future money. But what in the world is an imaginary interest rate? What could that second dimension possibly represent in economics? To figure that out, we have to talk about the word imaginary, because honestly, it's probably the worst branding in the history of math. There is nothing imaginary about it. In fact, it represents something very, very real. So think about it like this. If you're on a number line at the number 1 and you multiply by -1, what happens? You flip 180 degrees over to -1, right? It's a rotation. So since we know I times I equals -1, that means 2 I operations get you a 180-degree turn. So what must 1 I operation be? It has to be a 90-degree rotation. It's a turn into a new dimension. And what do you get when you keep making 90-degree turns? You get a circle, a rotation. You get a cycle. That's the secret. The imaginary part isn't imaginary. It represents rhythm, oscillation, seasons, things that repeat. It represents cycles. Let's go way, way back. Think about the most fundamental economic activity there is, farming. Is it a straight line? No way. It's a pure cycle. You plant seeds in the spring and your money goes down. You wait all summer, then you harvest in the fall and your money shoots up. Then you prepare for the next year. It's a perfect real-world economic rotation.
And that natural cycle created a huge economic need. Farmers needed cash in the spring to plant, but they wouldn't have any to pay it back until the fall. That gap right there is what gave birth to credit. And with credit came the credit cycle. The natural rhythm of the seasons became the foundational rhythm of our economy.
So now finally, we can build our Rosetta Stone. We can translate between these two worlds. Look at this table. The real part, which an engineer calls damping, like how a shock absorber damps a vibration, is exactly what an economist calls discounting, how value fades over time. And the imaginary part, which an engineer calls frequency, is what an economist experiences as cyclicity or seasonality.
You see, this changes everything. By using the engineer's perspective, we don't have to see economic growth and business cycles as two separate things anymore. We can see them as what they are, two parts of a single complex economic reality, one part pushing forward, the other part turning in a cycle.
And this isn't just a cool thought experiment. It unlocks a whole new toolbox. We can use engineering concepts like system poles to model when an economic cycle might spin out of control and crash. We can analyze supply chain shocks, understand the math behind bonds, and so much more. It gives us a brand new and incredibly powerful language for economics.
And to give you a sense of just how powerful this is, economists have identified at least 4 major, distinct business cycles, all happening at once. In engineering terms, each cycle is a pair of what they call poles. So to accurately model just those 4 known cycles, you need an 8th-order system. It's a way of actually measuring the incredible complexity of our economic machine.
And you might be thinking, okay, cool theory, but is anyone actually using this? Yes, absolutely. Bond traders live and die by a metric called bond duration. And what is it mathematically? It's the derivative of the bond's present value with respect to the interest rate. They are literally using the principles of the Laplace transform every single day to manage billions of dollars, even if they don't call it that.
At the end of the day, that's what this is all about. It's a shared language, a bridge. The abstract math of engineering becomes the tangible reality of profit, loss, and the seasons. It lets us stop seeing the economy as just this chaotic, unpredictable thing and start seeing it as a deeply complex system with a hidden and maybe even predictable rhythm.
Which, of course, leaves us with one last massive question. If the deep, rhythmic cycles of our global economy map so perfectly onto the same math used to design a circuit board, what other complex human systems out there, social trends, cultural movements, you name it, are just waiting for us to find the right formula to see their hidden frequency?